Good afternoon, everybody. I will be talking on cosmic structure in ghost-free scalar tensor theory of gravity, and thanks to the organizer for giving me opportunity to talk on our recent work, which has been collaborated with Nicola, Sabino, and Mattia. So I'll be talking on a screening mechanism, particularly testing screening mechanism in degenerate theory of gravity. And what is screening mechanism? So when we introduce modified gravity, then it introduces additional degrees of freedom, which often scalar, and which introduces a fifth force. So however, gravity is everywhere and it has to be tested everywhere, but it has been well tested in solar system. So we should recover the general relativity within the solar system. There are so many available screening mechanisms we have. For example, Vainshtein, chameleon, and symmetron also recently introduced this formal screening. And there are some review paper and some nice paper which I have came across during my study. And today I will be focusing on only Vainshtein screening mechanism, particularly on a recent model degenerate higher order theory. So when we talk on Vainshtein screening mechanism, what we want is that we have very large Vainshtein radius. Within that, we want to recover GR. However, outside that, we will have modification of the gravity, and particularly for the relativistic star or very massive object, for that it will be screened everywhere inside the object and also within the Vainshtein radius everywhere. So we expect that theory should be screened everywhere inside this Vainshtein radius, including the object, and outside we will have modified gravity. So we will be today we will be focusing on degenerate theory of gravity. And what is degenerate theory of gravity is that we put the constraint on the we write down all the possible terms until the quadratic, cubic, or quintic order, and then we put the constraint on this theory, constraint on the free parameters, and we restrict the ghost. So there is no ghost in this system, and we will be focusing on quadratic order today. And here the free functions are those blue, f, a, b, and this zeta 1 depending on x, where we are just considering shift symmetry. Now when I say quadratic, quadratic means that quadratic contraction or quadratic derivative contraction, covariant derivative in the quadratic order, it is contracted. So we can also add the cubic order and we can put the constraint. So under this constraint, this theory will be ghost free. So it will not give any higher order derivative, and it has been proposed by Anker, Langos, and Nogorim, and has been studied in the following paper in more detail. So what we are going to do is that our objective is that testing Vainshtein screening mechanism in this quadratic order degenerate theory. So okay. So the method, I am not going to talk on every detail. So I am just going to talk on method only. Then I will go to result. So we start a static spherically symmetric object embedded in de Sitter space-time for the quadratic degenerate higher order theory. Now we are assuming the background is de Sitter. That means that it will follow the flat de Sitter, but then we have to embed in spherically symmetric cosmic structure, and then we go to the sub-horizon and non-relativistic weak field limit, and where the perturbation will be also taken care of. So and if we take sufficiently large radius, I mean if we go sufficiently further, then all this perturbation will be 0, and we will have only the de Sitter background. So and if we close this, if we make this perturbation 0, so we will have de Sitter background. So we are going to follow this mechanism that first we put the de Sitter background and then we put the perturbation and embedded in spherically symmetric object. So considering today is Friday and everybody is happy to leave, so I directly go to the result. So the first result is that we have given the full covariant equation of motion so that the other people can also do the cosmology analysis or some other analysis. So we wrote the complete covariant equation of motion, and so that when we say degenerate theory in quadratic order, so it means that you can have like 3 different classes and also 4 different subclasses inside that. So if you use our this covariant theory and put the constraint, you can go to any different class of theory, but today we will be constraining our analysis inside class 1A. So the covariant equation are messy, it looks like this. It is just because it is very general. So you just put the constraint over this and you will get this. So I didn't want to show you the everything. So just look at our paper. So now result 2. So when I write down the gravitational force, what we expect is that we want to recover GR. So this is corresponding to the this is what we expect. But there is one additional term over here in the derivative of the potential. So what we expect is that if the Vainshtein mechanism is working, then this should be 0, this should be 0. So it breaks down. And what is m? M is the derivative. M prime is the derivative of mass distribution inside the matter object. I will explain one by one. So the fundamental point of view is that if this is non-zero, the Vainshtein screening mechanism is breaking down.
Is this a linear calculation?
Sorry?
Is this a linear calculation or is it linear GM?
Which one? It is linear, yes.
So you did a linear calculation?
Yes.
But then you wouldn't describe the Vainshtein.
We did the weak field. It is not linear, but we took the sub-horizon non-relativistic weak field limit. Okay. So the expression of this gamma 1 and gamma 2 are here, and G Newton expression is here. So here the model dependence is coming over sigma, and in another place in G Newton. So then what is happening here is that if we are inside the relativistic star or very massive object, so there will be the mass distribution will be varying. So therefore the m prime and n double prime inside the matter, it will be non-zero. Therefore these two terms will be non-zero. Therefore the Vainshtein mechanism will be breaking inside. However, just outside the relativistic star, but inside the Vainshtein radius, it is well screened, and outside it is modified gravity. So therefore that we are not able to recover the Vainshtein mechanism inside the relativistic star. So then what we wanted to do is that we wanted to put the constraint on the theory so that we get Vainshtein mechanism back and GR back inside the body as well. So the easy choice is that if we put the zeta 1 is the parameter of the theory, so parameter of the model. So now if you put this zeta 1 at 0 is 0, then these two terms become 0, then it will be becoming only the Newtonian force. So however, the zeta 1 at 0 does not mean the derivative of the function at 0 is 0. So therefore it is okay. So this is how we can recover the fully Vainshtein screening inside the matter as well. Probably it may help is in imposing constraint on the quadratic order degenerate theory on the coefficients. So yeah, people will be happy probably. Now there will be another case that where we partially recover the Vainshtein screening, which is not interesting, of course, that because the gamma 1 is still non-zero. I mean, but third one is interesting is that because when these two extra factor are equally, this is what is beyond Horndeski theory. So now if we use this condition on the parameters, then we recover the these two extra factor are equal, and we recover the this is actually beyond Horndeski theory, and this explained, I mean, the result has been obtained in these two papers, and we can recover the beyond Horndeski theory within our theory. So it says that beyond Horndeski theory and degenerate theory, in both of the cases, the Vainshtein screening breaks down. Now, the message you want to take to your home is that the Vainshtein screening mechanism breaks down inside the relativistic star for the beyond Horndeski and degenerate theory. However, within the Vainshtein radius, it is I mean, it is possible to recover by putting the constraint on the theory, and so possibly this is one of the way we can possibly put constraint on the free parameters in future. And we have the covariant result. If somebody wants to do analysis in another degenerate class of theory, they can just use our covariant equation and go to another class and do the same analysis, and let us know if it is if the result is something different. So and I thank to all of you for your attention, and if you have any question, I will happy to discuss.
Yeah, so I didn't get a feel of how all the corrections depend on distance and stuff, because the gamma 1 and gamma 2 must strongly depend on radius, right, or something?
Yes, it is. Actually, yeah, how strongly, if you want to give for beyond Horndeski theory, it is like 3 solar mass. If you put inside the center, then it is like very negligible. I mean, Vainshtein, I mean, almost you can recover the Vainshtein. I mean, the correction factor is very small if you put 3 solar mass or something like that. So this is how strong, I mean, if you want the number.
I mean, there's always a correction. It's just that
yes, it
in
is
the
just
normal
a
story, the gammas are,
yes.
If you want to define them like that, fine. They're very small contributions. So I mean, it's hard to get a sense from the way you've written it why it's not small. What's the difference between the normal case?
Well, we are actually presently doing more, I mean, numerical analysis, and where we can exactly say how is the numbers, how it is varying. Yes, but yeah, it is actually enormous if we don't put, like, if we just keep it in solar system, it is really enormous.
But so for what model is that? This is just
Degenerate, quadratic degenerate.
But there must be some coefficient of these operators I can choose, right, and set them to be
yes.
small.
Yes, this
the
is
normal ones.
So gamma 1 and gamma 2 goes to 0 if you run on density.
Yeah. So that's. So I'm just struggling to see that.
They are parameterized by the deviation, like alpha h, like by the deviation
Yeah.
of your density.
Okay.
And they are time dependent.
Yeah. So it should just be that you're putting a bound on these beyond Horndeski or degenerate terms, right? And they're more strongly determined.
Thank you.
So you're assuming that you're in the sitter, and I guess in terms of your scalar field, that means that you have only the first derivative with respect to time in your background solution. So do you have a sense of what would happen if you consider also second derivatives? Because we're not in the sitter.
Yes.
And at least in Horndeski theories, you have whole set of terms in the covariant equations of motion that depend on the second derivatives of the field.
Mm-hmm.
And these are usually ignored when people do these ansatz, this type of ansatz.
Mm-hmm.
Do you have something like that, or?
So you mean that I go to Horndeski? No.
No, in your theory. With the covariant equations, like,
Mhm.
are there terms that depend on the second derivatives that could change these solutions?
I see. I do have the I mean full equation, so we can see and talk. Yes. Thanks. I have to look at carefully each and everything.
Any more question? No, then
So Filippo was telling us that the FRW solutions for some of these classes are ruled out because the
Yes.
the tensor speed and the sound speed are
Yes.
opposite or something like that.
Yes.
So you're inside the class that works, or you're considering a wider thing?
Well, first of all, there are two things that we are in quadratic order, so that means that L5 of the Horndesk key is not contributing here, is not included. And the second thing is that we considered shift symmetry, and now I feel that it was not the correct choice, because many shift symmetry terms, as Miguel discussed, that will not be even for G4 shift symmetric term will be ruled out, right? If I am not doing mistake. In quadratic order G4, huh? Yeah. Yes. So only the phi dependency will be staying. So
Yeah,
in
but
G4.
then if you drop shift symmetry, then either you set phi equal to constant, in which case it's all these operators are 0,
Yeah.
or you have phi dot, which is what you need.
Yeah.
But then you have time evolution, and it's incompatible with the sitter. So I mean, you have to be shift symmetric. You cannot.
that
in
is
this setup, you have to be shift symmetric.
that is true. Actually, I agree.
Okay. Thanks.
okay, then thanks again. And we move on with
Thanks.